Good afternoon, my name is Orlando Moreira and I'm the Chief Architect and Fellow at GrAI Matter Labs, and today I'm going to tell you a bit about NeuronFlow, which is an architecture, a processor architecture that we have been developing at GrAI Matter Labs for delivering on the promises of neuromorphic computing. I'll start by giving a small introduction about what neuromorphic computing is, and then I'll proceed with discussing what kind of challenges we can address with our approach to neuromorphic computing and give an example of what we can do with our neuromorphic computing architecture and what it is. So what is neuromorphic computing? Well, essentially the idea of neuromorphic computing is trying to copy what the human brain does on silicon. Now you could ask yourself, why would you want to copy the human brain on silicon? Of course, there's always the interest of trying to build a model of something to understand how it actually works. And actually that's one of the big drives of neuromorphic computing, is this idea that we can use a model of the brain to understand better the inner workings of the brain. But if we think about a more a pragmatic approach, one that tries to bring to the market a solution for problems that we cannot solve otherwise, using the brain structure, so neuromorphic computing as a way of that will lead to actual efficient computing, we have to think what characteristics of the brain are we really interested in. And actually there are a few. I would say, if I try to choose the ones that I consider probably the most important amongst others, well, one of them is the scalability of the brain. One thing that the brain has is that essentially it is a very simple structure. You have neurons connected to each other by synapses. And that is essentially all there is to it in terms of structure. Then you just replicate this same structure of neurons connected to neurons over and over and over, and you increase the capability of your processing machine. So that's a very, very attractive proposition, because actually one of the problems that we always have when designing computer systems is scalability. So how do we grow from a processor to a multiprocessor, to a many-core processor? There are many difficulties there, because essentially we always think about computation in terms of the relation between the processing itself and the actual memory, and we tend to think about models of computation that are rather centralized in the usage of the memory, while the brain actually has a structure where all the state is actually distributed across all the neurons, and that is why it's so scalable. If you look at a common, a normal processor system like the ones we use in embedded systems, in laptops, in frames, one of the great difficulties is always actually this memory distribution, which is natural to the brain structure. Another big advantage of neuromorphic computing, and probably the one that I would like to discuss today the most, is related with power consumption. If we look at how the systems of the brain work, they actually are extremely low in power consumption compared with the processors that we design. Our silicon cannot even get close to the levels of power consumption that we get from a biological brain. So if we compare, for instance, a human vision system, so the part of your brain that processes visual information, and compare that with how much we spend doing the same thing on a CPU, you get almost 2 orders of magnitude of difference. So the human brain spends about 6 watts of power to process vision. A GPU will process in the order of the 250 watts. So we want to try to understand how the brain works, because we actually can gain a lot in terms of power consumption from it. So how does the brain do what the brain does? The basic model there is typically proposed to describe the structure of processing in the brain is so-called spiking neural networks. These are networks of artificial neurons that mimic the brain cell behavior. What they do is that they communicate with each other through valueless spikes. This is different from our typical artificial neural networks that transport values through the synapses. Here, no, we are actually transporting valueless spikes. It's just a signal that says I'm here, I'm not here. That's why it's normally referred to as a spiking network. They are fully event-based in the execution, meaning that you don't execute them layer by layer. It's just that every neuron has a state, and when that state goes above a certain threshold level, it will decide that it's time to spike. It sends spikes out through its synapses and then updates its state. So that means that all neurons in an actual spiking neural network model, they all have persistent state. Contrarily, again, to what we do normally in artificial neural networks, where you evaluate the output of a layer of neurons, pass it to the next one, and you can forget about what these neurons are doing. For most of the models, of course, you have recursive models, for instance, recurrent models that actually don't have that. But most of the models that are used actually assume that neurons are stateless and that you have a feed-forward network. In spiking neural networks, each neuron is stateful. It acts on its inputs, it spikes, and then it continues to hold state and continue to receive at the same time. And all the communication is synchronous and based on events. And one thing that we see often modeled is the temporal execution. So it is known that the signals take time to travel through synapses. That is an important property of the brain, and this is something that spiking neural network models try to model by actually assigning an amount of time that it takes for a signal to be transported by a synapse from a producing neuron to a consuming neuron. And it also, the state of the neuron, I told you that a neuron has a persistent state, but over time in a neural network, this state is going to decay. So it's going to start going down slowly. So if it is not excited again, it may actually go all the way down to an offset, to a bias. Okay, so this is what spiking neural networks try to emulate of the structure of the brain. That have been attempts of designing processes that actually fully mimic this basic model of the spiking neural network. But there are some tough challenges when you actually try to implement this sort of execution structure in silicon, because silicon doesn't have the same properties of the neurons in our brains. So actually, some of these properties are really not very efficient to implement in silicon. It's sometimes I say that the attempt of trying to build in silicon a brain that works just like the human brain is the same thing as trying to build with Lego a house that was designed to be built with actual bricks. Essentially, your basic construction materials are different, and because your basic construction materials are different, necessarily what is optimal in one type of material is not going to be optimal with another type of basic materials. So you get things like, so for instance, the idea of spikes. If you talk with a neuromorphic engineer, very often they will suggest to you that actually spikes are going to actually make your execution a lot more power efficient, because if you actually do your computation only using spikes, only sending ones and zeros, what's going to happen at the side of the receiver is that when you multiply by the weight of your synapse, actually this multiplication is just a multiplication by one, so you can remove that multiplication, and instead the only operation that you do is an addition to the potential of the receiving neuron. But actually, if you think about it, if you're working with silicon, we have extremely efficient ways of implementing memories. So actually, the state of your neuron is going to be implemented as a memory. And if it is implemented as a memory, you have to address it. And if you think about the size of an address, the amount of data that you have to send with the address is in the same order of magnitude and potentially much larger if you look at these large chips as the value. If that is the case, actually the overhead of sending a full value compared with sending just a spike is not very big. Actually, you send since most of the cost is in sending the address, you really don't save too much in the communication if you just send a pulse or if you send an actual word. And the other part is that, okay, you save a multiplication. Multiplications are rather power hungry indeed, but as I said, if you use a structure like this, most of your power consumption is actually not in the multiplication. Most of the power consumption in an operation is on the memory access. You have to read the state of the neuron, you have to read the weights, and you have to write the state back. This actually spends a lot more power than the multiplication that you have to do. So the advantage of the spiking model in terms of power consumption here is not that great. Also, very often you add this temporal behavior. If you look at the two main chips that are well known from big companies that invested on this, IBM's True North and Intel's Loihi. They both try to simulate brain time. They actually have a concept of global time synchronization that runs across the whole system, and then you simulate the time that the synapse takes to move information from an origin neuron to a consumer neuron by actually delaying this value, making it wait before it is consumed by the receiving neuron. But this requires very costly global synchronization. Your whole system has to operate at the same clock. And it also requires another thing that it is very expensive for silicon to do, which is the fact that you actually have to hold on to these values for a while. You have to actually store them in buffers before you deliver them. And every buffering costs silicon area as registers, as memory. It's not like the delay just means that we make a slower channel for the information to go from consumer to producer. It actually just means that we're going to have to store it while we wait. So it's not work conservative. Instead of processing something, we keep that value waiting to be processed just for the sake of following a particular programming model. And then there's another problem, is that if you talk about the idea that neurons have this exponential state decay is actually very easy to do in analog. Essentially, if you have a capacitor and you leave it be, essentially its current starts decaying. It's very different to do the same thing with a digital circuit, where actually I have to implement this decay by subtracting values from the register, which means reading the memory and writing it back, which is power. It's costly in terms of power. So we actually want to avoid doing that. Essentially, what we want to avoid is the pitfalls of biomimicry. So I normally give here the analogy of what happens with flying. We did discover that it was possible to fly by getting inspiration from birds, but for centuries we tried to actually make humans fly by mimicking what birds do, and that never worked. You have the example of Leonardo da Vinci's flying machine that tried to actually mimic what birds do by actually being capable of flapping wings. And that couldn't work because the materials that you were using to build your wings were not the same as the wings of birds. The whole mechanics of the body cannot be fully replicated with metal and wood. So we only actually made progress when we actually thought about wings that did not flap, which is essentially what the Wright brothers did, and that's how we managed to actually fly. So the question I'm asking here is, so what is actually the brain's secret sauce? What makes the brain good at low power that we can imitate? Now, I want to look at it from the side of I'm talking about low power, but why would we want to have a system with low power? Essentially, we are looking at edge devices. Edge devices are devices that work autonomously, that are responsive. They work in real-time environments where they have to immediately respond to the environment and to the user. Because they are autonomous, they typically have to run on a power battery, which means that they have really to be low power, and they have to be low latency. You cannot just offset them to a server. So we need very fast response times. Typically, they deal with continuous streams like camera feeds, audio feeds, industrial sensors, or biosignals. So if you look at this type of devices, what's the most important thing? It's low power, and it is a low response time. An observation about these systems, I told you that these systems have long streams of input data that is always on, that is continuously arriving, is that although a lot of data arrives, the actual information content of that data is relatively low. If we look, for instance, if we're interested in human speech and we look at the data that we receive from microphones, in a typical setup, you'll get 512 kbits per second from your microphones, but the actual information content of that stream is only 39 bits on average when somebody's speaking. When somebody's not speaking, actually the information content is 0. The same thing happens for cameras. So if you have a camera, you're getting 79 megabytes per second on a UXGA video. But actually, when there's no color present in terms of information, we are actually talking about zero information of interest. On another hand, if we think about the way we currently do the processing of these systems, we are kind of always doing what I would call a frame-based processing, a way of handling the input. We expect, we apply as an algorithm that works for an image. We will apply it to a sequence of image by just applying that algorithm independently to each one of the images in the stream. This is appealing because most of the popular camera sensors that we use, they are actually frame-based, so they send you a stream of pictures. And it's also simple and easy to scale. You just design an algorithm that works for an image and you apply it to a video stream. But do we actually consider the fact that if you have a video stream with several images, one after the other, most of them are actually just repetitions of the previous one, which means that actually we are doing a lot of redundant processing. We are looking at an empty road, we are processing the whole empty road once searching for cars, and in the next time instance that we receive the next frame, we do exactly the same processing again, and we do it over and over and over, essentially wasting processing power. So what I'm hinting at here is the idea of sparsity. If we look at any sensor that provides us data, the content of information is limited. I have here an example, for instance, of a road where a biker is moving around. Then if we are on the road, we may be just interested in the stuff that is moving around us. If I look just at the change that happens from one frame to the next in this image, because everything is still, from the first instant that we look at the system to the second instant that we look at the system, actually nothing changes. If you consider white everything that doesn't change, and other colors things that are changing from the first frame to the next, the only thing that changed was the position of the bike. So essentially this is the only new information that we have in the system that we should be processing, and yet we are going to actually process this frame over and over again. So what we see here is that there are several forms of sparsity, that is, of data that is not meaningful. We have sparsity in structure, that is part of the neural network that processes the image itself. So we know about that, right? You can prune many weights and kernels that are actually not used in the network. But you also have other types of sparsity. You have sparsity in space, which is that there are many areas on your image that have no relevant feature data, even when that data is changing. This normally is going to result, grosso modo, this is going to result in zero valid activations on your neural network. So that's what we normally mention as sparsity in space. There's a third type of sparsity, however, that it's not really exploited in any traditional implementation of neural networks, which is sparsity in time. The image changes little from instant to instant, but to exploit that sparsity, you actually would have to compute the differences between images, one that comes after the other. And this, in fact, is what our brain does. When we are looking at a scene, our brain is not processing over and over the whole image. It's actually just registering. It's an event-based camera that will register as events changes in the input, and it's going to process only that. And that is the property of the brain that at GrAI Matter Labs we're trying to exploit, and that's in that sense that we are neuromorphic, because we get an inspiration from this, although we don't try to slavishly mimic the behavior of the brain. How do standard DNNs process the image by all pixels to all pixels is essentially that you move the image through several layers of a network, and you're going to process everything that is in that image. But one thing that you could say, okay, but if any change, because everything is interconnected in the network, if something changes in the input image, then that change is going to require, because of the connectivity, that everywhere in the network I have to process everything. But that's not really true, because most of the networks that we use are convolutional. And in a convolutional network, if you think about a convolutional layer, if something changes in one input, you're actually this change in the next layer is only going to affect a relatively limited area, and due to the kernel around the pixel that has changed. And in fact, this means that most of the change is going to be localized, and it's going to be preserved downstream in the neural network. The same thing I can argue for pooling operations, where essentially I take one area and I reduce it to, I scale it down to a smaller area on a smaller feature map. Again, I'm preserving locality of change in the downstream. This suggests that when I process a neural network, if I try to process the change between two inference, instead of doing a full inference that I only process the change of the original inference that I made, I actually end up just doing everywhere. I have a kind of a change that goes through the network and only affects local change across the network. And that's exactly what we want to do. In a standard DNN implementation, you get image after image, and for each image, you execute all the neurons in your net, all the synapses and all the neurons in your network. You do this for every image, even if the change has, if the scene hasn't changed almost at all. What we propose is that for your first image, you actually do the processing of the whole image, you go through the whole network, but from then on, you actually compute the difference between frames and you only process the difference. So the second frame that you process, you're only going to process the events that represent the change that occur from another one. It means that you're going to do a lot less processing per frame, and we should get the same results. Therefore, exploiting sparsity in time. This, in fact, is what the brain does. It will process events, not full frames, and it will process only change. And that's why, actually, you require a network that is resilient in state, because you keep the state from the previous execution, and you just do a localized update of the computation that you did before, instead of computing everything over and over. So what we're proposing in our work is a model of execution of neural networks, of actual conventional networks. So we don't require that you write your application as a spiking neural network to start with. No, actually, what we propose is that you take a popular network, say MobileNet SSD or YOLO or something like that, and then what you do, you give us just the application as it is, already trained. And what we do is that we have tools that allow us to convert your original frame-based network into an event-based network, what you call a SparNet or a delta network. It's a network that is going to be able to process delta changes to your original execution. So the idea is that with this, we are going to exploit the time sparsity in a time series. The conversion is mostly automatic. We only propagate the changes, so we have a lot less work to do than with the original image. We require resilient neuron states. That's one of the costs. We have to keep the state of all the neurons in the system such that we don't need to recompute it. And you have to provide us one thing, which is a threshold, which is a minimum amount of change for each one of the neurons in the network that warrants the propagation of change. Because if you want to propagate all the change, you're going to get a lot of noise in the network, and you're going to do a lot of processing, just processing noise. So actually, you put a threshold that tells you how much change in one output is warranting a propagation of the change. So the essential part of the conversion of a normal CNN to our SparNet is just providing this threshold. And by the way, that's also the way that neuromorphic computing works. If you look at those neurons that I showed you, the spiking neural networks, exactly for each one of them, you define a threshold above which they spike by accumulation of the input. Okay, so what I showed now in this video here is what happens with the execution of our SparNet. On top, you see what happens, what a normal camera sees. On the bottom, you see here below, you see the difference frame. So it's a comparison of what changed in the last frame. A black means nothing has changed. And below, you see in red the amount of synapses that you have to process, of operations that you have to process for a normal CNN evaluation, and in blue you see the amount of synapses that we have to process if we do the delta frames. So you see a huge decrease in the amount of operations, especially when you're keeping to the same road or when you stop the car, and of course many more operations happen when you have to turn or when you go out of a garage into the exterior where the scene completely changes. So what we see with our SparNet is that the amount of operations that you can do that you need to do per frame is much lower than if you do it by processing complete frames. And this has several dramatic effects. So even at a reasonable 30 frames per second, the difference is already very large. We'll go back to those numbers later on. But it's particularly interesting if you think also what happens if you increase the frame rate. If you go for a very high frame rate with a conventional frame-based approach, you're actually going to linearly increase the amount of processing that you need, because if I get more frames and I have to process the full frame, I'm just linearly increasing the amount of compute by the frame rate. In our case, however, if I take the same exact scene, but instead of processing 30 frames, I process 480 frames, the amount of change that happened in that second is exactly the same. What I got is that I just got faster updates on my system, which means that I'll be able to more faster detecting that something has changed in the scene, therefore reducing my latency. But the amount of load, the amount of executions I need doesn't grow, because it grows a bit, of course, because of noise. Some change that is not really important, but if you have more frames, you're going to see more small unimportant change. But still, it's going to be in here, I think, from 30 frames per second to 480, we kind of increased the load by like 2 times, but nothing compared with what happens in this system that would grow for more than 15 times. So essentially, we can handle much higher frame per second, and because we can have much higher frames per second, we also are going to have a lower sampling period and therefore a lower latency. So does this have consequences? Well, we cannot anymore rely on our computer architecture being like the computer architectures that we designed before. The main difference here is that we have all this immense amount of storage that we still need compared with others, because we have to keep the state of all the neurons in the network. So this suggests an architecture with a distributed memory and with lots of memory. So essentially, it suggests that we do in or near memory computation. And of course, in the process, the frame structure is lost. So we are not processing a structure of data that is completely regular. We are now using a structure of data that is much more irregular, which means that we have a lot less locality of reference. We cannot cannot use so many sequential memory accesses, because we know we're not going through the whole image. So we lose some economies of scale there. So we need things like caching don't work as well for us. Network bursts don't work as well. DMA transfers don't work as well, because our network now works on receiving things that are more sporadic. We also have to do our scheduling in a different way, because instead of having a fixed structure of processing, we now have to do it event-based, which suggests data flow synchronization. I execute when I receive. I don't have a fixed structure of get this piece of data, execute, get next piece of data, execute. Is more reactive. Something arrives, I process it. Which leads us to the architecture that we propose, which is an array like the other neuromorphic architectures. We have a bunch of neuron cores. Each neuron core is an event processing machine, and these neuron cores communicate with each other by sending events to each other. How does each one of the neuron cores look like? Well, essentially, each neuron core receives events, queues them, and starts processing them one by one, goes to a synapse memory that checks all the neurons that are stored in this particular core that need to be updated, that are connected to this event. So you receive a value. When the value is received, you check all the connections of neurons for that event. You update all of these neurons by calculating their new states and writing back the state of each one of these neurons. And for each one of them, you also check if they go above their threshold for activation. If they go, then this results in a value that is sent to an external memory that checks to which other processors these values have to be sent to be processed by the next layer. This is essentially the basic architecture of Neuron Core and NeuronFlow Core. So we have actually made a demonstrator for this. We have a cheap hardware that implements a small instance of our architecture. It can only handle about 200K neurons. It has 196 neuron cores, and it's a modest piece of silicon with 20 square millimeters running at 500 megahertz. It is in our plans to make much larger machines, because if you look at this side, 200 million neurons, we cannot really have very big applications on it. So one of the things that we have been working on, and what we want to have in our product, is actually a dramatic increase in the number of neurons that you can have. while not increasing dramatically the area, actually with a very modest increase in area. So we know that we can do it, and we are working on it. I have here some results, but on view of time, I'm going to skip them. I think I wanted to show you our demonstrator. I will.
We have created an autonomous navigation scenario using a gaming engine. A camera observes a road in real time and feeds its frames to GrAI One. GrAI One processes the input scene using a neural network called PilotNet and updates the steering angle for a car. This information is received by the gaming engine, and the steering is updated in real time. As the car navigates this road, it is constantly updated with the steering information. As can be seen on the screen, more than 95% of the scene is relatively similar as the car moves on the road. This represents a real-world example of time-based sparsity. GrAI One only needs to process the changes in the scene from frame to frame. This allows the system to consume very low power and process a fairly complex task of autonomous navigation. In this setup, GrAI One consumes less than 50 milliwatts in total power to execute this task at 25 megahertz.
Okay, so this I guess was explained in a bit more organized way than I would do it myself. Let's look then at the results here. So we run this PilotNet application on TensorFlow first, where we trained it using common tools, and we measure how many operations per frame we needed to do by computing all the synapses, and that gave us 5 million, roughly 5 million operations. By using GrAI One and not doing time sparsity, means we continue to feed all the frames complete. This was to measure how much spatial sparsity we had. So sparsity that is not because of the lack of difference between subsequent frames, but because of lack of information of interest in the image. We reduce by a factor of 2.7 the amount of computation that we want to do. And our architecture is very good at this, because essentially, if you have a value function that doesn't send an activation, nothing happens. We don't have any memory accesses. We don't have anything. So we truly save everything that this operation would cost. And then we have the experiment where we actually try to do spatial and time sparsity in GrAI One. And there we really go rock bottom with the amount of operations for the same stream running. And this was at a very modest frames per second. I think it was at 10 frames per second that we took these values, which means that the difference would actually increase if we go to higher frame rates. We actually have only 260K operations per frame. This means that, in fact, what we had was a reduction of 20 times in the amount of computations that we had to do, and the amount of computations is essentially going to mean the amount of time that it takes. Of course, that we get a bit more error in our computation, and this happens because essentially, since we are putting these thresholds, the thresholds are making the system less sensitive to change, which means that here and there we are going to actually not get as exact results as we would get in TensorFlow. However, the extra error is very modest if you compare it with the original augmented data error of the TensorFlow scheme. And you have to take into account here that it's also a dynamic system. So when you try to measure the error, if we actually committed an error in one frame and we turn a bit too much to the left, in the next frame, we are going to have to commit an error in the opposite direction to correct. So that kind of exacerbates the error number that you see there. In any case, is negligible. Of course, you could choose lower thresholds to get more accuracy, but more operations, or you could also increase more the threshold if you're not so interested. If you can live with a lower accuracy, you increase the thresholds per neuron, the amount of change that they will require in order to send the change to the next factor, and then you would get a bit more error, but you would also further lower the amount of operations. But here we are already at 20 times, so we think it's already a very good result. So in conclusion, so the NeuronFlow architecture is designed to exploit sparsity. In that sense, it is a neuromorphic architecture because sparsity is we believe to be the essential secret sauce of the brain, the fact that we only process change and not the whole information all the time. It also kind of, the structure that we have in our neural network execution, our SparNet, is very similar to a spiking neural network in that all the neurons have internal state and the communication goes through events, and there is a threshold always. in each neuron that decides when you spike or not. We don't use other ideas from neuromorphic computing that we didn't see direct applicability of, and don't allow us to go from an application as we know it, like a standard network like YOLO or MobileNet, to an implementation. And it exploits several types of sparsity in structure, because event-based activations actually skip very easily the zeros weights, because they simply don't generate event executions. There's sparsity in space, because zero-valued activations will actually not send anything out, so there's no access to memory, there's no communication, there's no processing for a zero-valued activation. And while in many other architectures you may skip the computation, but it's very difficult to skip the actual memory read, because you have first to go to the memory and read it and see that it's a zero before you actually skip it. And sparsity in time, which practically no other architectures that I know of, or commercial ones at least, support, which is the idea of computing the differences between frames instead of computing always full frames. So that concludes my talk. If there are any questions, I'll be very happy to answer them. Thank you very much.
Hey everyone, we're back from Orlando's talk. Thank you very much for the presentation. We were talking to Orlando in the green room before we joined, and we have a fun fact to share. We learned that Orlando is a specialist in not only neuromorphic models, but also in the epic confrontation between Batman and Superman. He actually lives in a constant state of doubt between Superman and Batman, almost like two kids for whom it is impossible to put one over the other. Orlando, about this, I have a question. How did you feel about the movie Batman versus Superman? By the way,
yeah, I hated it. I think it's a terrible movie, and it creates a completely fake conflict between two superheroes that actually typically are friends. And normally, if they fight each other, is either because one of them has been controlled by some power from outer space, or because it's an alternate reality where you have an evil version of either Superman or Batman. So it's a pretty bad movie. And then the way that the fight stops is actually because suddenly they realize their mothers have the same name.
Yeah.
Really? I mean, that's how you solve the problem between two people. Your mother has the same name. It's beyond bad. I knew it was going to be bad, and it was even worse than I was expecting.
Honestly, it was a disappointment for me too. Do you have any favorite fights between the two, by the way?
Yes. So if you look, for instance, at a cartoon, an animated movie called The New Frontier, they also fight each other, but actually it's a ruse to actually make people think that Batman is out of commission, but actually he's just in hiding. It's actually a pretty good one. And there's one where the two of them fight against all the other superheroes. So that's also a very good animation movie. It's Superman and Batman. I forgot what was the name of the movie, but they fight against the whole DC universe, the two of them, and of course they win.
And it doesn't have Ben Affleck, so I guess that's a good thing.
No, that's always a plus.
Okay, I already burned two questions, but I had to. So everyone, let's start with the Q&A. We have Orlando back with us, if you didn't notice already. We will be reading directly from the questions you have been posting online based on the number of votes. Okay, so let's just jump right into the first one. First question is, what are the current major?
Yeah, so I should start by explaining that I'm not per se an expert in neuromorphic computing. I'm a computer architect, and I'm designing a computer based on ideas that we got from neuromorphic engineers. But the goal of our work is actually taking ideas from neuromorphic computing and making them work in a practical way. So having a product using these ideas. If you look at normally what is pointed out, the main practical advantages of neuromorphic computing, they tend to be related with reacting to a changing environment and fast processing, so event-based. Exactly what I explained in my talk. So for instance, one of the things that you'll hear a lot is about event-based cameras. what happens in an event-based camera is that instead of having the frame structure that you send full frames of information, the camera, what it does, it detects that there has been a change. It only sends events to signal that some of the pixels have changed. That is one area where there's a lot of research, and the applications they try to go are applications that have that component of a changing environment. So typically applications that that are going to I think I already said this, interact directly with the environment. So vision system is one of the main ones. Auditory system also. There was a detail that I wanted to mention, but somehow I lost it right now. So maybe it will come later. About current major research. So I think that the main two, actually, there are kind of two main areas of neuromorphic computing. There's neuromorphic computing that actually is only interested in modeling the brain. The objective of their work is actually trying to understand how the brain works by modeling it. They are not really trying to make a practical application of it, just you imitate in order to understand. That's not the branch I'm looking the most at. I'm looking at the one where we actually try to look at practical applications on neuromorphic computing, and within there are kind of two main branches still. So we try to do computers based on silicon still, because that's the material we understand, that's the material we have used for computers for a long time. But there are some people that are going to do it using analog circuitry and digital circuitry. And the advantage of analog here is that analog has that thing that, for instance, decays are natural to analog computing. One of the things I mentioned in my talk is that these neurons have a state that decays over time, exactly to imitate the human brain. And this decay is very easy to implement in analog, but very difficult to implement in silicon. So it's expected that analog models actually will be able to mimic the brain closer than digital. The problem, or more efficiently, closer and more efficiently, because it could always imitate anything in digital, but it would be less efficient. But what happens if you do it in analog is also that all the cool methods that we have to reproduce a chip to have mass production, they don't really work that well. The miniaturization and mass production don't work well in analog the same way that they work in digital. And because of that, it's difficult to make it commercially competitive. And that's also why in our company we decided to go with digital.
Okay. I want to pick this topic that you just mentioned about the biological systems and the brain as an area of research, and connect it to the next question that we have, which is actually about exactly this topic. So since neurons are able to conduct electrical signals, do you think we would be able to develop a biological neuron-based chip with these living cells? I know you're not a biological systems expert, but your
I guess that's the answer. That's the answer you're going to get. I haven't seen any research in this area until now, and to be totally honest, I'm a computer architect. So the way I look at it is there's here a computation model, a way of executing an application, and I'm trying to deliver with the concepts of digital systems that I understand, and the concepts of computer architecture that I understand, try to provide a way of executing that model the most efficiently possible. And since I'm interested in a practical application, I drop anything from your model that it's not going to help me. That was actually one of the points I tried to make in the talk. If there's a characteristic of brain that is there, but I don't understand how that helps me making better computations, I drop it. There's no reason to model something just because it's there, only if I can gain something from it.
There you go. And that connects perfectly to what we were talking about in the opening session about our talks. No bullshit and just honest experience. So thanks for that. That's a perfect answer. More of an opinion question here. What, in your opinion, are the top universities in research offering a master's or PhD in this area, neuromorphic computing?
Oh, let me see the ones I'm connected with.
This is probably for someone who's interested, maybe starting, wanting to go for this.
So my knowledge, of course, I have some connections within the domain, although, again, part of the point of the talk that I was giving was that we are actually kind of steering away from the main branch of neuromorphic computing. Actually, we essentially concentrated everything that we do on one concept coming from neuromorphic computing, which is the concept of sparsity and exploitation of sparsity. And that, I don't know if you notice in the talk, but actually what happens is that we start from another point, which is let's just isolate what works here. And then we start from sparsity. And then when we design an architecture to use sparsity, we end up with some of the same concepts that neuromorphic computing is using. So we have, again, neurons with state, and we have all the issues around propagation of events and all of that. But we are essentially steering away a bit from the idea of neuromorphic. We don't start from neuromorphic, we start from the advantages of neuromorphic. However, of course, we have some contacts with some universities here, so I would guess the ETH in Zurich, there's a group working on it there, and actually they are also associated with a startup that is trying to do something a bit similar to what we are doing. In Sevilla, there's also a group working on this. I now have a kind of a blank in my mind, so I forgot the name of the professors. I remember their first names but I cannot remember their family names because I know them in a personal basis. If anybody is interested, you can just send me a mail afterwards and I give you their names. I think those are two very strong institutes working on that. There's also a group in Australia. There are a couple of groups in the US, but if I think about the ones that I have seen the most research of, I would say ETH and Sevilla.
Okay. So I hope for the person who asked this question, there will be.
Please contact me. I do have some contacts to give you, but I cannot right from the top of my mind now say that it's going to.
There you go. You're getting a direct contact here. So I guess annoying Orlando in the event platform will maybe open a few doors. I don't know. Maybe make it easier for you.
Yeah.
Orlando, we have to wrap up, but I want to ask this question also because you were saying that we were kind of diverging away from the basic concepts of neuromorphic computing. And I actually have a question about that. What, in your opinion, are the basics, very basics, for someone who wants to deep dive on these concepts on neuromorphic computing?
The basics of neuromorphic. So the idea that you have something like a spiking neural network model, which is event-based, meaning you don't propagate like we do in artificial neurons. Normally you propagate per layer, right? You execute a layer, then the next layer, then the next layer. Neurons are just kind of computation blocks. They don't keep state. In neuromorphic computing, the neuron has state, the neuron stays. So it's kind of an interactive computation mode. And these events are coming and going around you. And there's a concept of time associated with the computation. So I compute now, and later I'm going to update the results of my computation. Those are essentially the most basic ideas. But if you think about it, they change very fundamentally the way you think about it. In our case, actually, what we did is that we just started from your artificial models, the normal ones, so to say, and then we execute it in a way that looks like neuromorphic. But we don't start, our original model is not a spiking neural network as others. But if you understand those concepts, you will also understand what we do, vice versa. Probably for people that are coming from more standard neural networks, understanding our neuromorphic way, our SparNet, is going to be an easier way, an easier introduction than starting directly with full-on neuromorphic models.